Hello, let's look at lesson 1.2 and beginning the chapter 1. And this chapter is all about limits. We're going to talk about how to find limits graphically and numerically today. Um, the objectives you can see are posted right here. Estimating a limit using numerical and graphical approach. Learning different ways to see if a limit can fail to exist, and then we'll study the formal definition of a limit as well. So just giving you an idea of an AP question, this came from the 2016 exam. You're given a diagram of the function f, and question 83, which would have been under a calculator section, it says the graph of function f is shown above. At what value of x does it have a jump discontinuity? Well, jump discontinuity would be right in this vicinity, wouldn't it, where we see that vertical jump going on from one function leading into another function. So I would have to answer, what, about 7? So I would say C7. Limits are super important. You're going to find that in calculus we do nothing but talk about limits, especially when we're defining a few of the key tools used in calculus, such as a derivative, which won't make much sense yet, or an integral. Those are founded on what is a limit, and so limits become very, very important to us. So let's just see if we can base this next question off of your knowledge from pre-calc. Here is our function, and you can clearly see we've got a rational function, x squared minus 2, and in your head you might think, well, I can see that that does factor. So maybe you are factoring that in your head. And then I'm looking at that denominator thinking, well, there's some issues with the denominator. I certainly would have a problem when x was 2. So for this function, we see that they're excluding the number x equaling 2, mainly for a domain issue, correct? So why is x not equal to 2 included in this function definition? Well, it all has to do with domain, and the domain cannot include x being 2, but it can include all other real numbers. So a way to analyze this problem when I ask, what is the limit as we get close to 2, I'm asking you, well, if I graph this function out, what would that function look like as I get over here at 2? Well, we know there would be a hole because 2 isn't defined, but what would be this height? What would be this y value? So one way of investigating it is to look at a numerical table. And here I've given you some suggestions for letting x equal a few of these values. What I'm trying to do is build from the left and the right side and come in close to 2. And we can analyze then what are those values as I get closer and closer to 2. So I've put them in my calculator. If you want, please go to your y equals key, go y sub 1 equals, and key in this rational function. Then I would next go to your table and turn it to the ask function. And that you do by going into using the blue key, second, and the window key up there in the functions, so second table set. And you should be able to flip your table to an ask mode, and then you will be able to go to the table and key in these particular values. So I'm going to just hit pause a minute and fill them in. So once I put in these numbers, I can start seeing a trend. It appears that as I'm moving towards the value of 2 as an x value, my y values, or my f of x, which, is really representing y here, my y values are increasing as well. Once I hit 2, when I hit that on my table, I noticed it said error, which is not surprising because we knew that x could not equal 2. And then as I proceed to the right side of 2, as 2 gets larger, 2.001, 2.01, 2.1, my values of x are 4.001, 4.01, 4.1, and so on, and then continue to grow. So I can kind of look at this function from the left side of 2, meaning looking over here, and then the right side of 2, kind of focusing on what's happening on the directly to the right of it. And I can get a feel for, I think this function is getting close to 4 when x is at 2. And indeed, that's how I would answer this question. I would say the limit as x approaches 2 of my function f of x is equal to 4. This is a y value, isn't it? This is looking for a y value of a y height. So a y value going in there. And here you can see the definition of a limit. If the y value of a function f of x becomes close to a single value L, they're using L to represent a number, the limit. As x gets closer and closer to a point C from both the left and the right sides, then the limit of f of x as x approaches C is L. And that can be written using mathematical notation. So all of this phrasing is a lot of words, of course, but it means the limit, we're finding a limit, as x gets closer to C. In our case, we were getting closer and closer to 2, so you'll see my C here says 2, of some function. We could write that function in there. We could elect to go the limit as x goes close to 2 of x squared minus 4 over x minus 2, if I remember that was the function. Yeah, it was. And that equals some value. What value does that equal? Well, when I compare back up here 3.99 to 4.001, I would have to say, you know, an educated guess, that's got to be coming in close to 4. And so that's what they're saying, let L be, is that y value, the limit value. Graphic approach. Graphic approaches are wonderful because you can just visually look at the function that's graphed and pick up what the limit is. For a limit to exist at an x equals c value, we would know that the value from the right of that c value must also equal the y value that we're coming in from the left side of x equals c. So I get this, you notice I got the hands pointing here. My left hand must come at the same height as the right hand is if I'm following my graph. So let's just take a look at this example. Use the graph to find the limit as x approaches 2. Once again, we're picking up a c value, that's 2, of the function g of x, where g is, and now they're going to define g of x. They define it, we can see we've got this brace here, which kind of indicates, oh, this is going to be a piecewise function. Indeed it is. When x isn't equal to 2, the value is 4. And when x does equal 2, the value picks up -1. So how would that look graphically? Maybe pause and see if you can write this out, graph this for me. Well, when I have y equals 4, I know that is a horizontal line, right? So I'd have a horizontal line up here at the height of 4, 1, 2, 3, 4. Horizontal line everywhere where x isn't equal to 2. So I've got 1, 2. I'm going to put a hole right there because it's not defined as 4 when x is 2, but it is 4 for all other values of x. So I get this horizontal line at a height of 4. When x is 2, we pick up the y value, that y is equal to -1. So up, not over there. At 2, I'm going to be plotting down here at -1. So now my function, let's see if I can erase, I'm going to erase that too. It's in the way. All right, so here's what my piecewise function graphs out like. Now, what is that limit as x approaches 2 of g of x? What is that L value that we're headed towards? Is there an L value? Well, when I just kind of trace from left and right, as I come into x being 2, so I'm kind of thinking, okay, here's where x is equal to 2, correct? As I come into that from the left side, I'm at a height of 4. And when I come in from the right side of x equals 2, as I approach this vertical imaginary line of x equals 2, I'm also at a height of 4. So 4 equals 4. That means that my function, of course, is 4. Left equals right. In order for a function or a limit to exist, the left side must take on the same height as it does from the right side of my C value. One-sided limits. I hope you discussed one-sided limits last year as well. They always exist unless it is going to infinity or negative infinity. So here we have, suppose we have a graph of f of x again. And notice that the function below does not approach the same y value as x approaches c from the left and the right side. So here's my x equals c mark. And I do notice I've got one height of k for y and another height of L for my y value. And so definitely these functions are, there is a jump discontinuity going on here, correct? And if I trace starting from the left of C, so as I trace over this coming in, I notice I pick up a height of k. They just didn't give us any number, so we're going to just use some variables to represent that. When I trace it from the right side, so as I'm coming into this c value of x being c, as I approach this, I notice that this height is coming in at L. So sometimes we're only interested in what's happening from one side versus the other side, and that has particular notation as well. So if I'm coming in from the right-hand limit, where I'd say the limit of f of x as x approaches c from the right, I would write it as the limit, and we just kind of abbreviate limit, as x approaches c from the right side. So we go c with a superscript of plus behind it. And then my function was written as f of x would equal some value. You know, who knows what it is. Left-hand limits, if they want to ask just from the left side, I would say, okay, what's the limit as x approaches c from the left side? And I'd indicate that with a superscript of a negative of f of x equals something. And the general limit is written as the limit approaches, as x approaches c of f of x would equal, you know, some value. This implies, when I write c, that I have looked at two cases, that I have analyzed what is happening from the right side of c, and I'm also paying attention to what happens on the left side of c. These two would have to take on the same value in order for that limit to exist. All right, so, oh, we get a nice picture here. Lots going on in our picture. I see jump discontinuity. I see hole discontinuity. And then different, you know, horizontal line. Looks like we got a portion of a parabola. We've got more linear functions going on. So quite a bit going on this thing. I would like you to do this on your own. In class, we probably would work this as partners, but see how many of these you can answer. So just hit pause and take a moment and walk through these. Okay, welcome back. F of 2. Hopefully you figured out that f of 2, let me see if I can get my pen back. F of 2 is where I'm looking at x equals 2, right? When x is 2, so I've got this purple line, vertical line I can move. So I'm just kind of setting it on x being 2, right? And I want to know where the function is defined at 2. That's going to be the solid dot. So for this one, it will be an answer of, let's see, -1 is that height of that solid dot. When I look at f of -1, I can move my purple line over here and looking for where is that function defined when x is -1? Well, that value is 4. So 4 is my answer on that one. F of 4 from the left. I know it's from the left because I see that superscript of a negative. So now I'm going to move my purple line over to 4. And I keep in mind that I'm coming in from the left side of this, so I'm kind of approaching 4 from the left side. What height did I turn out to be? Well, that height looks like it is 3, so the appropriate answer is 3. This one is saying the limit as x approaches 2 from the right of f of x. You should practice saying this as well, because, you know, saying verbally out loud can often help you in math understand the problem a little bit better, strange as that is, that just saying it aloud can make that much difference. I want to approach from the right-hand side. I know that because I see that plus sign. From the right-hand side, my answer is going to be 1. F of x from 2 from the left side. 2 from the left side means I'm coming in to it from this side. That has a height of -1. -1 is my next approach. So I'm going to move my purple line over to -1. You know what? I would like to make that just a little bit less. Yeah, let's fade that a bit. Okay. I want to come into -1 from, originally it looks like from the right side, because I see that plus sign. So from the right side, I would be coming into -1 when x is -1. This vertical purple line where my approaching is coming into, it looks like our height is going to be called 2. So that equals 2. How about from the left side? Okay, so now left side, I want to come at it from this side. It too comes in at a height of 2, doesn't it? Awesome. Well, if the left and the right agree, as they do in here, that limit does exist for x approaching -1, and it is 2. -4 from the right. So I'm going to take a moment, relocate my vertical line, because that's the focus for my eye, from the right side of 4. So I'm bigger than 4 coming in from the right side. Right side would bring me towards this. Oh, that has a height of 2, doesn't it? I'm just looking for that y-axis, height of 2. From the left side of 4, so I would be following my function. Oh, wait a minute. There's no function defined over here. This one does not exist, DNE. The limit as we approach -1. Okay, so what they really want me to look at is from the left and the right side of -1, correct? I've got to have both of them agreeing. So I'm going to look from the right side of it, as well as I'm going to look as x approaches -1 from the left side of -1 of f of x. So from the left and the right side, I have a height of 2, right side, I have a height of 2. This does have a solid answer. It is 2. And we did that analysis from the right side, and we did that analysis before from the left side. Both came in at 2. All righty, just a couple more to go here. The limit as we approach 2, and I'm going to look at my previous work. Here was 2 from the right. Here was 2 from the left. 1, -1. 1 does not equal -1, does it? So this is a does not exist limit. At 2, when it states just 2, not from the right or the left side, then we need both the left and the right side to agree. We have a jump discontinuity at x equals 2, therefore the limit does not exist. What about as we head to 5? Okay, I'm going to take and move this purple line over to 5, kind of get myself oriented. And I notice that there's an arrow on my function, so in my head, I'm extending that line so that I can read it at 5. At 5, I am going to estimate, I'm probably awful, well, maybe I shouldn't do that. Yeah, no, I think it does. I think it hits at -2. Do you? I'd say my answer is -2. Left and right side are approaching -2. At 0, when x is 0, so focus that vertical line. This is, you know, when x equals 0 here. When x is 0, where's my vertical line crossing my function? at -1. And then our last one is they want us over at 1. My vertical line, which represents x equals 1, intersects the f of x function right about here, and that height corresponds with -2, so I would answer -2. Hopefully you got all those right. Existence theorem, there are different ways, or well, there's really only one way that the limit exists at c. We talked about it, and that means that the limit as x approaches c from the right of f of x must equal the same y value, the same height, when x approaches c from the left side using or following my function. So left side must equal right side, or in this case, I guess I've got right must equal the left side, correct? In order for our function to exist at c. No longer talking the one-sided limit, we're talking full-fledged at c. Limits can fail to exist in 3 situations, and our first one is when the left side does not equal the right side. And we're talking about one-sided limits here. So given this picture, boy, I notice right away I've got jump discontinuity at -1. That would mean the limit does not exist at -1. This is the equation that we're working with. It is an absolute values function divided by x plus 1, and it will graph out in these 2 linear horizontal lines split at x equals -1. So from the right side of -1, well, that would be when I'm on the right-hand side of -1, because I want to be bigger than -1. It looks like my height is 1, doesn't it? I can see the height right here coming in at 1. And then this horizontal line has a height of -1, so from the left side of -1, it is -1. And the first thing I notice here is 1 does not equal -1, so the right-hand limit doesn't equal the left-hand limit. And so the limit as x approaches -1 of f of x is a does not exist. And that would be my conclusion on that one. The limit at c being -1 does not exist. Another way that a limit can fail to exist is when you have oscillating functions. And that oscillation is occurring, at x equals c. So for this particular one, as I approach 0, this thing's just going wonky on us. It's vibrating so quickly that it really is actually very hard to see the function. So it is not settling on any one particular value from the left and the right side. This would be a function that the limit as x approaches 0, in this case, of our function, they named it f of x, so f of x, this would be a does not exist as well. Third situation where a limit fails to exist. This means that the left side doesn't equal the right side, and that is this case here where we see the function on the left side going straight up to infinity. From the right side, it's skyrocketing, it's going to infinity, so we're headed to infinity from both sides. So this would be unbounded behavior is how I would describe this. I have my function when x is c being unbounded. That is an x there. There we go. When x is c. You could say at x equals c. Bad word there, bad writing, at c. So from the right side of 2, I get infinity. From the left side of 2, I get infinity. I could describe this function as I approach 2 as going upward, right? That it is approaching infinity. That is an answer. However, that is not a number. That is a concept of largeness. And therefore, we really, truly have a limit that does not exist. But if I want to get more descriptive, I could tell you that as I approach 2, my y value is headed to infinity. Lastly, I think this is our last thing besides the practice there. Lastly, we want to sketch a graph to satisfy each of these conditions, and that's kind of fun to do. So f of a is undefined, so this means when x equals a, we don't have an answer for y, right? We don't know what y is. X equals a is a point discontinuity. I know what point discontinuity, that's the same as a whole discontinuity. And we have the limit existing. What does that imply to me? Well, it tells me the limit from x approaching a from the right of f of x is equal to the limit as x approaches a from the left side of that function f of x. So I'm going to just give myself a wild x equals a spot here. There's x equals a, believe it or not. I know f of a is undefined, so I'm just going to open up a hole there, get that whole discontinuity in place. And then I am going to make the limit exist, and I'm going to do that by bringing in, hey, you know what, I think I'll do a linear function. Linear function, let it leave at the same height, and therefore the limit from the left and the right side of x equals a certainly exists. It's coming into some height here. You could call it L, couldn't you? So the limit exists. F of a does not exist because I've got the whole, and that gives us this point discontinuity. Awesome. Let's look at the second example here. The limit as x approaches a of f of x does not exist. Okay, then I can take this information here. I want to see if I can pull this over. Should be able to. Yes. Becomes D and E. Okay, the only thing I've got to do is say, hey, this does not equal. The limit from the right side doesn't equal the limit from the left side of A. It has a jump discontinuity. I know how to do that. And f of A is undefined. Oh, okay, so f of A, let's give ourselves A again. So some value of x being A, I made it a positive. And we know the limit doesn't exist. So I would have to come into A at some height and then leave A at a different height, wouldn't I? And I'm just going to do two simple linear functions. You could use parabolas if you wanted to. That'd be no problem. I want to make sure that f of A is undefined, so I'm going to go open circle and open circle on this. Therefore, A is never defined. I don't have, some spot where it was defined, giving it, a solid dot. I'm going to refrain from doing that and just leave them as open circles so that it is not defined. That would fit that description. All right, so part of your homework tonight is to go home and complete this. We'll check that in class. And the next thing is I want you to go on to Delta Math. This is my teacher code. So you're going to go to deltamath.com and you're going to create a student account. And I would love for you to format your username like this. So, you guys, this was last year's. You guys will be 20, Alex first name, dot Olson last name, something like that. Cindy.Oppold would be fine for me. And password is your 6-digit student ID, or if you have to zero fill because you're a 4-digit student ID, do that. And then let's use capital first name initial, capital initial for your last name. And go ahead and get yourself in by creating an account, make it a student account, and you should find the first homework should be like 1.1 or 1.2 part 1. All right? And you've got probably a couple days to do that particular thing, but don't get behind. Do your work tonight, then tomorrow's lesson makes so much more sense. That's all I have for you. Tomorrow is part 2. Have a great evening.